Hey Phys 1 kids, Campbell here. In this video, we're going to talk about the law of conservation of energy. Now, we've already talked about how the energy of a system changes when we do work on a system or when work is done and we lose energy to the system. Now, we can rearrange this equation to come up with a before and after perspective, an initial versus final perspective of energy. So energy initial plus whatever work is being done equals the energy final of my system. So in this unit, we're going to deal with things like kinetic energy, gravitational potential energy, spring potential energies. Those might be in the initial part of our equation, plus whatever work gets done by whatever external force there is. That's going to equal the final energy of the system, which will be kinetic or gravitational potential or spring potential, whatever's going on at the end, plus possibly some thermal energy. So that leads us to what the law of conservation of energy is. The law of conservation of energy says that the total energy of an isolated system is constant. So the energy initial equals the energy final. Those values are the same. I'm just transforming energy inside my system. Now, if we go back to the momentum unit, remember we talked about an isolated system is one in which there are no external forces. So that means that there's no work being done on the system, so there's no energy being transferred into or out of that system. Instead, the energies, the different types of energies are being transformed from one kind to another. So how do we choose systems? Well, some of it is just really intuitive, and it's really based off what information you have in a problem that you're trying to solve. So let's take a look. So for example, an object that's falling in the absence of air resistance. So I drop a ball, and if we thought about what the free body diagram would look like in the absence of air resistance, we just have that force of gravity vector, the weight vector, pointing straight down. Now, if you think about what that is, that's the force of the Earth on the ball. So if we just choose the ball as our system, then our energy equation is just kinetic energy as the ball falls, and the Earth, which is applying this external force, is doing work. But if we choose the ball and the Earth to be the system, now all the forces are internal to that system. So we're just transforming one type of energy to another. So we're transforming an initial gravitational potential energy to a kinetic energy as the ball falls. Now, this is one thing that's really important. I want you to write it down. In order to use gravitational potential energy in your equation, the Earth must be part of your system. Because if it's not, that means that that force of gravity, that weight vector, that is an external force. What about an object sliding down a ramp? A frictionless ramp versus a friction ramp. Those are different. If it's frictionless, if you think about it, the only force the ramp itself is applying is the normal force, right? That's the force between the surface of the ramp and the object. And that normal force is perpendicular, so it doesn't do any work. But there is a force of gravity on this, so if we include the object and the Earth in our system, then again, we're just looking at conversions between types of energy, gravitational potential and kinetic energy. If we have an object that's moving and it compresses a spring, if we choose the object to be the spring in the system, then all the forces are internal. And so what we have is kinetic energy that's being transformed into spring potential energy. The last scenario here is an object that's sliding on a surface that has friction. If you think about what's happening, right, it has kinetic energy because it's sliding, but it's going to eventually stop because friction is taking energy out of the system. Now, if we just choose the object, then we have work being done by friction because that would be an external force from the surface. But if we choose the block and the surface, then all those forces are internal, and instead we have kinetic energy being transformed into thermal energy. So let's look at a little more detail about how choosing a system affects the energy equations. A good example is a person riding a bike up a hill. Right? If you're riding a bike up a hill, you're putting energy in to get to the top of the hill, and then energy comes out maybe as you're going down the hill. But the total energy has to stay constant, or we have work being done to increase the energy. So let's take a look at a system being just the bike. and the environment being the person and the earth. So if the bike is a system, the bike can only have kinetic energy. So when you have just a single object can only have kinetic energy. Remember, in order to have gravitational potential energy, the earth has to be in your system. So if we just choose the bike, that means the bike's kinetic energy is changing, and how it's changing is that the person, right, is pushing on the pedals. So they're doing work by applying a force to the pedals, causing the bike to go up the hill. So that person is doing positive work, putting energy into the bike, into the system. But if you think about the other force on the bike, it's the force of gravity, right? If he stops pedaling, that bike's going down. So the other external force is the force of gravity, which is the earth acting on the bike. And that produces a negative work, right? That would pull energy out, right? He stops, he goes back down the hill. So the person is transferring energy from himself to the bike by doing work, applying a force over a distance. And the earth is taking energy out by applying a force, the force of gravity times the distance. So our energy equation would be the work done by the person minus the work done by the force of gravity, because that force is opposite of the motion direction. And that total work is equaling a change in kinetic energy of the bike. Now, that would be one scenario where we just chose the bike as a system. But you know what? Let's put the earth in the system, and then we can use gravitational potential energy. So if this time we choose the bike and the earth as our system, and the person will still be our environment. So this time, the person is applying positive work, right? They're applying a force over a distance in the direction of motion. And that work changes the kinetic energy of the bike, but it's also changing the potential or the gravitational potential energy of the bike earth system. Now, why would you do this? Well, sometimes, like if you're just given information about the force of the person pedaling, then you would want to use work is equal to a change in the energy of your system. Now, one thing I want you to notice is that this change in kinetic energy here is the same as this here. It's not like these values are going to be any different depending, because we chose a different system. But instead, if you think about what we have here, work, remember, is force times distance. And remember that work, that force by the force of gravity, right? The force of gravity is equal to mg, right? And if work is force times distance, then for my force of gravity here, right, we would have mg, and the distance, right, would be like maybe the height of the hill. And here, right, the equation for gravitational potential energy, right, is mgh or mgy, or just the height, right? So the work done by the force of gravity really looks like gravitational potential energy. So it's not like we have a different equation. It's just really how we classify the energy transfers versus the transformations. Now, what if we put the whole thing in the system, the bike, the earth, the person? Now all my forces are internal. And so now all the changes are just transformations. I am changing kinetic energy into gravitational potential energy. And that's coming, these changes are coming from this expenditure of chemical energy in your body. So now instead of work being done by the pushing pedal person, it's coming from the chemical energy that's being spent by the pedal pusher person. So I know this sounds kind of confusing, but honestly, when we start to work on problems, it'll be kind of just instinctive what you choose as your environment and your system. So let's try some examples. Here I have a person sliding down a water slide, and she starts at a height of 9 meters above the ground. And she starts with an initial speed of 2 meters per second. Now we're going to say the slide is frictionless because friction, right, that adds a whole new dimension. And I want to know, how fast will this person be traveling at the bottom? Well, when you solve problems for energy, what I want you to ask yourself initially, is there height? Is there speed? Is there a spring? Is there work? That'll be in your initial energy equation. And that will equal the final energy because the total energy of a system is constant. And so in the final conditions, you're going to ask yourself, do you have height? Do you have speed? Do you have a spring? And was there thermal energy generated? So was there friction? So let's do that. For our initial condition, do we have height? Yes, according to this problem, we have height. We're 9 meters above the ground. So we're going to choose Katie and the Earth as our system. And so we're going to say that we start out with some initial gravitational potential energy. Do we have speed? Yes, Katie is traveling at 2 meters per second. So that means we have an initial kinetic energy. Do we have a spring? Nope, no spring. Do we have any work being done? No, I don't have any information about forces, so we're going to say there's no work being done. There's no friction, so I don't have work being done by friction in this case, and we put the Earth in the system, so gravitational potential energy is not outside of the system. So that's my initial energies. My final energies, do I have height? No, I don't have height because I'm at the ground. I'm at the 0 point, my 0 reference point for gravitational potential energy. So my final gravitational potential energy is going to be 0. Do I have speed? Yeah, if you think about sliding down a hill, right, you have speed when you get to the bottom. So do I have kinetic energy? Absolutely. Do I have a spring? No, there's still no spring. Is there any friction? No, this is frictionless, so I don't have to worry about thermal energy. All right, now we just got to plug in our equation. So the gravitational potential energy, right, is mgh plus 1/2 mv squared for kinetic energy, and that's equal to the final kinetic energy, so we put an initial there, 1/2 mv final squared. All right, now we just got to put in numbers. Now, one thing you're probably wondering is, well, you know, Mrs. Campbell, you didn't give me any information about mass. Well, if you think about it, if you divide both sides by m, right, the m's cancel. Don't need m. All right. So let's now plug in numbers. G is 9.8. The height initial was 9 meters. To that, I'm going to add 1/2 of the initial velocity squared. So the initial velocity was 2 squared, right? Don't forget this half, so we got to divide that by 2. And that's equal to 1/2 times the final velocity squared, and that's what I'm trying to find, final velocity squared. All right, so now it's just a matter of doing some math. 9.8 times 9, 2 squared, which is 4 divided by 2 is another 2, so we're going to add 2 to that. We're going to multiply everything by 2 to get rid of the half, and then we're going to take the square root. So if you do that successfully in your calculator, you are going to get 13 meters per second. So ask yourself, what types of energies do you have initial? Is there work? And what types of energies do you have final? And is there friction? One last example. So here I have a woman pulling her daughter up a hill in a bike trailer. The trailer and the girl have a mass of 25 kilograms, and the slope is 100 meters long and 4 meters high. On the slope, this woman is pulling with a constant force of 8 newtons, and they start at the bottom of the slope with a speed, so I have an initial speed of 5.3 meters per second. I want to know, what is their speed at the top of the slope? Well, in this example, since we're given information about force, we don't want, and the force that Monica's applying to the bike, we don't want Monica to be part of the system, because we need Monica to do work, to transfer energy into the system of the trailer and her daughter Jessie. So in this case, when we ask ourselves questions, we are going to have work because we are given force information. So we're going to do same thing, energy initial equals energy final. Our initial energy, do I have height? No, at the beginning, we don't have height. Do I have speed? Absolutely. At the beginning, I have speed, so I have some initial kinetic energy. Do I have a spring? Nope, still no spring. Do I have work being done? Absolutely. I have work being done by Monica. All right, those are my initial energies. What are my final energies? Do I have height? Yes, I do. Afterwards, I have a height of 4 meters. So that means that in the final case, I have gravitational potential energy. Do I have speed? I should, because that's what I'm trying to calculate is the speed. So that means I have final kinetic energy. And do I have thermal energy? Well, it doesn't tell me anything about thermal energy. So we're going to say no. Oh, and I still don't have a spring. So energy in equals energy out. What do you have? And in this case, if we want to talk, if we wanted to label, and I don't know that it's critical, but whoops, sorry. If we want to label the system is the trailer plus Jesse and the Earth, right? If we are going to use gravitational potential energy, then we have to use the Earth as part of our system. And then our environment is going to be, sorry, that's supposed to say environment, is going to be Monica, because which is the pedals, she's applying a pedals, force to the pedals to push the bike up. All right, so my initial kinetic energy is 1/2 the mass of the trailer plus Jesse times the initial speed of the trailer plus Jesse. The work is force, right? The force applied by Monica times the distance that the force was applied. That's important. It's the distance, 100 meters. Final, my gravitational potential energy would be the mass of the trailer and Jesse, the gravitational acceleration, the height that they traveled, and then my final kinetic energy, 1/2 mass final velocity squared. All right, I'm going to rearrange this so that we can solve for velocity. So I'll keep it in variables, and then we can go back and put numbers in. So I have my 1/2 mv initial squared plus that force applied by Monica times the change in distance. From that, we're going to have to subtract the gravitational potential energy, so we're moving that over, and that's equal to 1/2 mv final squared. So that means my final velocity is going to be the square root of 1/2 mvo squared plus the force Monica applies times the distance minus mg h final all over 1/2 m. All right, let's put some numbers in to this lovely equation. All right, we have our 1/2. The mass is 25. That initial velocity was 5.3. Don't forget to square that. The force is 8 newtons. Oh, sorry about that. The distance it travels is that 100 meters. It's not the height. It's the actual distance the force was applied. From that, we're going to subtract the mass, 25 times 9.8, and I'm running out of space here. 4 is the height, all divided by 1/2 times 25. All right, so now it's just a math exercise. So if you plug this into your calculator and you solve for the final velocity, you should get 3.7 meters per second. Hope you got that. All right, we're going to do some more practice when we get to class, so I will see you in class.